Alright guys, so this is your help video for this week's integral review worksheet. You have this already. It's in your 2.2 notes, so hopefully you guys kept that and have it stored up somewhere. Might want to get that out and have that handy, especially when we do our integral review quiz coming up soon. So just a lot of different integration strategies, and it's kind of helpful to know how to use each one. So whenever you have problems of this sort, when you're integrating a 1 over x to the n, if that n is a power of 1, in other words, if you're looking at something like this, it's x to the first power in that denominator, then that turns into an ln. That's a natural log. Okay? Now, whenever it's any other power, anything except 1, then the first thing that we do is we bring it up to the top, change its sign, and then we add 1 to it and divide by that value. Okay, that's just the power rule, right? So two different situations that look very similar, but you do deal with them differently, okay? Now, other things, rational expressions. So anytime you have like a polynomial over a polynomial, there's a lot of different situations and different integration strategies for each one, and that's what part 2 here really kind of helps us to flesh out a little bit. Okay, so U substitution is going to pop up in quite a few of these, but basically how the U substitution is going to work is anytime the power of your U is 1 more than what's ever in the numerator, then that's probably going to be just a U substitution problem. So for instance, suppose I have the following. Notice how this power here is 1 more than the power in the top. That's an indication that you're going to be doing a U substitution where the U is equal to the denominator. Okay? That's probably what that situation is going to be there. Now, we have learned 3 different arc-trig functions. There's arcsine, there is arctangent, and then there is secant. All right, so now arcsine, the integral looks like this. You may have a number on the top, but for now I'll just put 1. But you have a square root, and the a is, you have a number that's a perfect square here minus a variable that's being squared there. That's what arcsecant integrals look like. Arctangent integrals look pretty similar, but they don't have a square root, and it's a plus in the bottom instead. And the order of the letters doesn't really matter. The u squared could come first, or the a squared. It doesn't really matter on the bottom. So there's that. Next, we have arcsecant. Arcsecant, once again, it could have a number in the top, but ultimately what really matters is that you're going to have your variable in 2 places. You're going to have it once outside the radical and once inside the radical being squared with a minus and then the a squared. Okay, so that's what the arc-trig integrals look like, and then whenever you integrate them, they look like what we have over here. Okay, and so that's another one. Now it's possible to use u substitution with these, and we might see one of those in some of our examples that we're doing today. So it's possible that you do u substitution. And when you do, your u will probably be one of these things here, okay? And we'll talk about that when we get there. But it's possible to do u sub with arc trig functions, all right? Now completing the square. Completing the square happens whenever you have a number in the numerator of some kind, but you have some kind of a trinomial on the bottom. Okay, we're going to do completing the square, and it usually results in an arc trig function. And specifically, it results in an arc tangent. So we'll see that example in some of the problems that we are doing coming up soon. Finally, we also have long division. Long division happens anytime that the polynomial in the numerator it has a power that's greater than that of the denominator. So for example, if you had like x cubed plus 2x minus 1 over x squared minus 5. So in this case, you'll notice that the power in the top is greater than the power in the bottom. In that case, you're going to want to consider doing some long division. Finally, you have splitting the numerator. This one's kind of hard to notice. So if you have a polynomial in the numerator that has a lower power than the denominator, okay. Now that's the same thing as u substitution, and so a lot of times they could also be u subs, and that's what makes them a little bit tricky. But I think what'll make the splitting the numerator a little bit different is that, you know, even though you may have a lower power in the numerator than you do in the denominator, let's say we have that, it's possible that when you have two terms like that in the top, so let's put that in there, more than one term in the top. When you have more than one term up top, what you're going to do is you're going to split it up into two separate integrals. One where you have x over the denominator, and one where you have 1 over the denominator. And after that, you have two separate integrals that you're just going to work on separately. Like this one here, that's a u sub problem because the denominator's power is 1 more than the numerator, so that's this guy. But this guy here, that's an arc tangent. So you would do each one of those separately. But the strategy I'm getting at mainly here is that when you have two terms in the numerator, it's possible that you can split it up. Now, technically, we could have done that here also. I could have split that numerator up, right? But I just know that since the numerator has a higher power than that of the denominator, if I were to split it up, it's not going to help me very much in the end. It's not going to work out well. So for this one, long division is the way to go. And so we'll see all of these in the examples that follow. So once again, on the teacher examples that I'm going to be working out for you, I'm not doing the problems that you have, but I'm going to be doing problems like them. The first couple problems we're going to be looking at have something in common, and that is the fact that they're all arc trig functions. You could tell. Compare this to the arc trig functions that I just went over in the previous little slide. This is clearly an arc secant. So arc secant looks like this. We have 3 blanks that we need to fill in. I need to find something that goes here, here, and here. Okay? Let me color code it actually. Oops, that was too much. Didn't want to undo all that. What goes here is going to be different than what goes in the other two spots. These two red spots are the square root of the number here. So that number down there is a squared. So a squared equals 1. That means that a equals 1. And that's what's going to go here, and it's also what's going to go here. The number that goes up here on the top, that's going to be this. So that's going to be my u. U is equal to x squared, and I'm sorry, not u. U squared equals x squared, which means that u equals x if you take the square root. And so we're going to put an x right there. Now to write this out a little bit more simply, we're going to have the 1 over 1. You don't really need to write that, so we can ignore that in this case anyway. And then we have the absolute value of x over 1, but once again, you don't need a 1 in the denominator, plus c. So that would be our answer to number 1. So you have to recognize what kind of integral you're dealing with. Okay, I recognize that fits the arcsecant pattern. And then from there, based on arcsecant, take the square root of this, that tells you the u, take the square root of that, that tells you the a, and just put them in the right spots, and you're good to go. All right. Now, your number 1 may not be an arcsecant. It could be an arctangent, or it could be an arcsine. You have to look at it to know. It's up to you. So I'm gonna, in the next 2 problems, I'm going to have each one of those myself, but it's up to you to recognize them. So now let's take a look at this one here. Now this one's a little bit more challenging, but let's back up a little bit. Go back to number 1 really fast. Remember how I told you that you could find your u by taking the square root of this number? Well, when it comes to arcsecant, there's another way. That's how you do it for most of the arc-trig functions. But for arcsecant, there's another way. The u is just this number right here. So I want to show you why that's beneficial to recognize that. In this case, it's a little bit hard to see the u, but that's my u. And so with this one, anytime this is more than a square, you're going to have to find out what your u is. In this case, you can see it right there. But the way you rewrite it is anytime that number there that's under the radical is more than just a second power, we have to rewrite it as a second power. And in this case, what to the second power would be 4x to the 6th? Well, it's this number right here. So that's easy for us. Now, sometimes you just figure it out yourself, but there it is. Now, whenever you have to do those kinds of problems where it's more than a square, and so you have to rewrite it as a square, those are problems where you have to do a u substitution. So my u in this case is the one that's in the parentheses. And I do need to take the derivative of this with respect to x. And then I need to get the dx by itself. And then I need to rewrite it again. And in this case, I want you to notice something. My u is in 2 spots. So I'm going to replace 2x cubed with u here and also here. And I'm going to replace my dx with du over 6x squared. And these cancel out. And now that I've done that, it fits the pattern that we need it to fit a lot better. Okay? So, now if you ever still have a number up here, by the way, like let's say it was like 5. Let's say I had a 5 up here. If you ever have something else up there, all you're going to do is you're going to take it out and put it in the front and put a 1 there instead. Okay? Now in this case, I don't have to do that, but I'm just telling you in case you see something like that. All right, but let's review. So anytime you're dealing with something that looks like an arc-trig function, but this number here is more than a square, you have to rewrite it as a square, and as a result, you're going to have to do some kind of a u substitution. After you've done that, it should look like a much simpler type of problem. It should fit one of your arc-trigs almost exactly. And so once again, this is another arcsecant. So the pattern is 1 over the square root of the number, arcsecant of the absolute value of the square root of this number over the square root of this number again, plus c. Don't forget your plus c. And of course, we do want to go back and replace that u with what u originally equaled. It's 2x to the 3rd. Okay? Now, you can probably just leave your answer like this. That would be fine. There is a simpler way to write this answer, however. So let me share that with you. Could come up as a useful piece of information. Not promising it will, but it could. So first of all, you can take the absolute value of 2 separate from the absolute value of x cubed. That's a property of those. And the absolute value of 2 is 2, so the 2's just cancel. But you do want to leave that x cubed in the absolute value bars. You have to. Okay? The 2 I could take out and reduce it. That's fine. To tell you the truth, I don't think the software I use would do that, so it doesn't matter if you do that or not. But what does matter is this, is that x cubed has to stay in parentheses. Anytime this number here is odd, you've got to keep the absolute value. But if it's even, you don't need the absolute value. So like, let's say that this was an x to the 4th instead. In that case, you might find they don't have absolute value bars here anymore. They might just have parentheses. And that's because absolute value bars just make things positive. But that's the same thing that happens whenever you have an even power. The even power makes it positive anyway, so you don't really need the absolute value bars. So that's a subtle detail. Now, I think I know my testing software pretty good. I don't care how you write your answers because it's going to be a free response, but if you ever had a multiple choice, I just want you guys to be aware of the different ways that this answer could be written. Let's take a look at another one. Now, as you can see here, this one, we have some issues, right? It's like, well, it's not a basic U sub problem because this power is not just one more than this, so I can't do U sub. But it does almost look like an arctangent, but remember, when you're doing the arc-trig functions, this has to be a square. It can't be a 6. But we talked about a way to fix that last time on the last problem we just did. In that case, we could just put a square out here and ask ourselves, okay, what can I put in here so that when I square it, I get x to the 6th? That way they're actually the same thing. Well, what squared is x to the 6th? That would be x to the 3rd power. Now you'll notice that this power is one more than this power, and now we do get to do our U substitution. So this is going to be a U sub problem that results in an arctangent. So the 3x squared is going to stay here. The 1 plus, that's, so we're going to replace this x cubed with a u. So now we have u squared, and there's supposed to be a dx here, my bad. And we're going to replace the dx with du over 3x squared, and the 3x squareds cancel out, and we're left with 1 over 1 plus u squared du. And now that's a much cleaner looking arctangent problem. So now with arctangent, we have 1 over a blank arctangent of a blank over a blank plus c. Now, the bottom two blanks are the square root of this number, which is 1. And the top blank is the square root of this, which is just u. And we don't really need these 1s anymore. Anytime your fraction is 1 over 1 or the denominator is 1, we don't really need to write those. So we can just put arctangent, and u in this case was x cubed. And there you guys have it. So that would be the answer to 3. So those are the arc-trig function ones, the first 3 that I gave you. And on your worksheet, they'll also be, those first 3 will all be arc-trig functions. Some of them are going to require you to rewrite the higher power as a square and do U substitution immediately afterwards. But remember, the real skill here is not so much in doing that in and of itself, but also recognizing, oh, that is an arc-trig problem. Because technically, you're not going to know that when you're taking your test, which one's an arc-trig. You have to be able to recognize them by the form they take. All right, let's go ahead and take a look at number 4. Now, number 4 is a little bit different. Now, you might think, okay, well, that looks a lot like an arc-trig also, doesn't it, Mr. Bailey? We have a number here with a thing. So can I, if I rewrote that as a square, will it work? Well, no. First of all, you can't really rewrite 3 as a square. That's kind of an issue. Also, even if you could somehow rewrite this as a square on the bottom, the problem is that whatever it is, it's going to be less than 3. The power will come out to be less than 3. So And U substitution only works when this power is greater than the one on the top. So this is not an arc-trig function. Kind of hard to tell, but it just won't work. It just won't work. If you tried, it just wouldn't work. So, but what we do notice is that it's a basic U sub problem. Anytime the power on the bottom is already, at the very beginning, one more than the power on the top, then it's not an arc-trig function. It's just a basic U sub problem where you make the entire bottom equal your U. Take the derivative. Get that dx by itself. Do your U sub. I'm going to replace the entire bottom with U, and I'm going to replace the dx with du over 12x cubed. Now, sometimes these numbers won't cancel out all the way. Like the number on the bottom may not cancel anything out, but that's okay. Those numbers don't really matter. In this case, they do cancel out, but if you ever have something left over, numbers are okay. You can just take those numbers and move them out to the front. But what you definitely need to cancel out at this point are the x's. So the x cubes need to go away. And I also don't really care for having this negative inside. So I'm going to move that to the outside, and now I'm left with 1 over u du. Now when you have 1 over u to a first power, that's an ln problem. So it's going to be negative ln absolute value of u plus c. And my u was 3x to the 4th plus 4. So how did I know to do a u sub problem? Because this power was 1 more than this power. In that case, you just make the entire denominator equal to your u. And when that happens, a lot of times it will turn out to be an ln problem. It may not, but a lot of times it can. So let's go ahead and move on to another problem here. Let's go ahead and take a look at this. Now, this next problem is also a u sub problem. Not because the power in the denominator is 1 more than the numerator, but because of this. Another way to identify a u sub problem is because the derivative of the denominator is in the numerator. So for instance, when I'm looking at this problem here, my denominator is tangent of negative 5x. Well, the derivative of tangent is secant squared. So that's another indication that you're going to be doing u substitution, where you make the bottom equal to your u. So in this case, my u is tangent of negative 5x. The derivative of u with respect to x, well, this is going to be a chain rule. The derivative of the tangent is secant squared. And the derivative of the inside is negative 5. And once again, we want to get that dx by itself. And then we're ready for our u sub. So the top is going to stay the same for now. The bottom is going to be u. And the dx is going to be du over negative 5 secant squared of negative 5x. Now the secant squared 5x goes away, and the negative 5 goes into the 10 negative 2 times. And as I've said, when you have a number up here other than 1, just go ahead and throw it out to the front of the integral. Numbers can come out, variables cannot. You're allowed to take numbers out of integrals, though. That's what we learned about in Chapter 6. That's what we call property, I think it was property 3. But anyway, once again, we have another ln situation on our hands. So this is going to be ln of the absolute value of u plus c. And our u was tangent of negative 5x. And there's our answer there. So it's another u sub problem. As you guys can see, u substitution is very common and useful strategy. And it's going to happen again here. Now, this is another u sub problem, but it kind of breaks the rules a little bit for the last one, because that worksheet I went over with you was talking about rational expressions, and this is not a rational expression. This is an exponential function here. And when you're dealing with exponential functions, the u can be in different places, but a lot of the times it's just going to be the exponent itself. And in this case it is, because look at that power. That power is one more than this one. And that's another indicator. So let's go ahead and do it. My u is going to be x to the fourth plus 3. The derivative of u with respect to x is going to be 4x cubed. Get that dx by itself, and let's commence with the u substitution. So we have 4x cubed, e to the u, and then du over 4x cubed, and these cancel, and now I've got this. Now the integral for an exponential function is that it stays exactly the same, but we do want to replace that u with what it originally was. And so there's my final answer there. All right, so for number 8, we're going to notice that I have a trinomial in the bottom, and that's our indicator that we're going to be doing that thing called completing the square. So what does that work? How does that work? We haven't done that in a little while. Completing the square means I want to turn this trinomial into a perfect square trinomial. And the way we're going to do is we're going to take the 5 and we're going to push it off to the side over here, because I want to create a number that's different from that right here. And the number that I want is going to be exactly half of this number, which is -2, squared, meaning raised to the second power. And that's what I want to put there. So -2 squared is 4. Now I don't want you guys to get the mistaken assumption these numbers are always identical. They're not. It's half squared. Okay. Now the reason for that is because when you factor this thing, x squared goes here, 4 goes here, x times x, 2 times 2. They're both going to be negative. That way they combine to make the middle. So when you factor this thing, you get the same thing twice, which means that it's squared. Now, I just added a new number in here, which changes the value of the expression. So you're not really allowed to do that. But you are if after you add it, you also subtract it. So I'm going to also subtract it over here. And so when I do that 5 minus 4, then I'm left with 1. Now that's a very convoluted and long explanation, but there it is. Okay, so that's what we call completing the square. Now, let me try to make it a little bit faster for you guys, though, because it doesn't need to be that hard exactly. Okay, but that's basically the explanation of what's going on there. So what we do is we take our polynomial here, and like I said before, you're going to take half of this number, and you're going to square it. Put the answer here. And you're also going to subtract it over here. So you put it in 2 spots. Now, these two numbers combine to make 1. We have a shortcut for factoring perfect square trinomials, though. A perfect square trinomial is a trinomial where when you factor, you get the same thing written twice, so it's a square. The shortcut is it's always going to look the same. It always looks like this. The only thing that's going to change is the number that goes right there in the middle. And that number will always be half of the middle. So you could save yourself some time instead of doing that box method factoring strategy, and just know it's always going to look like this, where the number that goes here is always half of the middle. Okay, so that's kind of our faster way to do it. So it's really just a 3-step process. Complete the square and put it here as well. Combine those. Shortcut for factoring. Okay, so that's what we want to do. And so the bottom is going to become the following. It's going to be x minus 2 squared plus 1. Okay, so you want to complete the square. And how did I know to do that? You do that anytime you are looking at a trinomial in the denominator. That's probably going to be the strategy to go with. And in those cases, it's going to end up being an arctangent function, an arctangent integration problem, where the u is equal to whatever's in the parentheses. So now my integral will look like this: 6 over u squared plus 1 du. And once again, we don't like that 6 there in the top, so I'm going to go ahead and take it off of the top and move it to the front, like that. And now you guys can see more clearly that that's an arctangent problem. So you complete the square, and then it's an arctangent problem after that. So we have the 6 in the front, and then for arctangent, we do 1 over the square root of this number, which is 1. Arctangent, the square root of this number, which is u, over the square root of number, which is 1, plus c. We don't need these. And the u is x minus 2, right? And so the final answer here would be the 6 is still in the front. Arctangent of x minus 2 plus c. Now some of you guys might be wondering, Mr. Bailey, shouldn't we distribute the 6 into the c? Well, technically you can, but this c represents just some unknown constant. And so if you multiply an unknown constant by 6, you get another unknown constant. So you might as well just leave it as c, which represents an unknown constant. So you don't have to worry about the c really in this case. All right, let's go ahead and take a look at number, I skipped 7, silly me. Let's go back and do number 7. So notice that the power on the top is greater than the power on the bottom, and there's multiple terms in the top. When that happens, that's a splitting of the numerator problem. So I'm going to take the first numerator term and put it over the denominator, plus, and then I'm going to make a new integral. The next numerator term over the denominator, plus, and another integral, -8 over the denominator. That's what we call splitting the numerator. So anytime the power in the top is greater than the power in the bottom, and there's multiple terms in the top, that's an option to consider. All right, so simplify. X to the 4th over x to the 3rd here will leave me with 5x. X squared over x cubed will leave me with 1 over x. And here we could take that -8 out into the front. And also, anytime you have a 1 over an x to a power and that's something other than 1, we're going to do the reverse power rule. So actually, I'm just going to get this ready now, and I'm going to change that to be x to the -3. And now we're ready to integrate. So for this one, we add 1 to the power, and we divide by that number. This one is an ln problem. And the next one, we're going to add 1 to the power, and we're going to divide by that number, plus c. We have a little bit more simplifying to do. These can reduce each other, and let me erase to make some space for myself here. So -8 divided by -2 is a +4, and also it's x to the -2, which means it really just goes to the bottom, and the rest of it's just going to stay the same. And there's our final answer. Okay, so that's a splitting the numerator problem. All right, the last 3 problems we're going to look at are definite integrals, meaning that we're not just integrated, but we're actually using the second or the first fundamental theorem of calculus to calculate the value of the integral, which is basically like finding the area under the curve. Okay, so first of all, I'm going to take this negative out and move it to the front like so. And the integral of secant squared, if you remember your trigonometric integrals, is tangent. Then we go ahead and do our plugging in. Tangent of 0 is 0. And tangent of pi over 6, I believe, is radical 3 over 3. And so the final answer is negative radical 3 over 3. Then we have just a regular polynomial. So let's do that one. Integration is first once again. So you add 1 to your power. And then you put that number in the bottom. So it's going to get multiplied with the 2 that's already there. The next one, we add 1 to the power and divide by that number. And the last one, we're just going to put an x next to it because it's a constant. And then we're going to simplify this. So we have negative x cubed over 6 plus 2x squared minus 4x going from 5 to 1. The next step is to go ahead and plug in our numbers that they give us. And I don't like how I'm writing that. Okay, so the next thing we're going to do is we're going to plug in the 5 and the 1 and subtract those two things. And that would look like this. And then we're going to simplify that. On the left side it looks like that, and on the right side it looks like this. Going to need to distribute the negative in here. So now I've got 125 over 6. I'm going to put those together now, save myself a little trouble. And then over here, after distributing the negative in, this becomes a positive 1/6, a minus 2, and a plus 4. And so I'm going to combine all the normal numbers first. That's going to give me 32. And then I'm going to combine the fractions next. That's going to give me negative 124 over 6. And then I wonder if we can reduce that. Well, I know that we can reduce this. Let me reduce it a little bit. I know 2 goes into both of those. So negative 62 over 3. Getting a common denominator. Multiply the 32 on the top and bottom by 3 so we can get that common denominator there. It's going to be 96 over 3. And then if we combine the negative 62 with the 96, we're going to have 34 over 3. Let's hope I did that right. There's so many places you can go wrong here, but I got it. Yay, 34 thirds. All right. All right, and then we have one more problem. Darn it, I showed the answer. Don't want to show the answer yet. All right, my only purpose in including this one is to show you how do you do U substitution, or how do you do a definite integral that involves U substitution. So in this case, this is a U sub problem where the U is this. So let's work that out. Okay, well, with definite integrals, you have to remember to change the limits also. So you need to plug negative 2 in, and you also need to plug negative 4 in to your U expression to transform those values into U values. So this one's going to be 0, so the negative 2 becomes 0, and the negative 4 becomes 2 doesn't equal negative 4. Okay, so that's negative 4, I think. It doesn't change, so I guess it stays the same. That's interesting. All right, and there's that. So that's one thing I want you to be aware of, that if you ever have to do U substitution with a definite integral, you have to change the limits also. All right, another thing is that little 2 there in the bottom. I'm going to move it here to the front, like so. And then from there, we can go ahead and... So now we're going to do our integral. The integral of e to the u is e to the u, right? That half is going to stay in the front. And we're going to plug in the numbers they give us. And e to the 0 is 1. And e to the negative 4 is 1 over e to the 4. We'll go ahead and distribute the half in there now. I mean, honestly, at this point, it's fine. If you wanted to stop, you could. But you could also get a common denominator by multiplying this one on the bottom by e to the 4th and also on the top. And then by putting them together into a single fraction, you can end up with e to the 4th minus 1 over 2 e to the 4th. But I don't know. It's kind of extra to me. But just in case you get a multiple choice question where you need to do that, that's how you do it. All right. But the big aha here is that when you're doing a u sub with limits, you have to change the limits using the u equation also. All right, so that's it for our integration review. We'll definitely be covering more integral stuff later on, but for now, that's going to be sufficient. So until next time, see you then.